3 of our quadratics units. Now we're going to actually start graphing quadratics. And you've been introduced to the form of quadratics, which is y equals ax squared plus bx plus c, where a, b, and c are any real number, but it's just a can't be 0. So this is the general form of the equation. Usually when we're given something like this, we are going to just graph by using a table of values. But first, I'm going to show you the parent function or the base function, and that's y equals x squared. So this is your baseline for all quadratics. And then afterwards, if there's any other numbers or terms added to it, like your bx or your c, all it does is transform the graph and shift it up and down, left and right, or stretch it. But this is your foundation of that graph. So we're going to start off by finding what this graph looks like using a table of values. And I'm just going to pick numbers from -3 to 3. Honestly, you can pick any number you want, but because you're squaring it, your y value will get quite large if you already have a large x value. So I'm just going to start with the middle as my 0, and then it can go up to 3, and then go down to -3. So I'm picking these points just because they're relatively small, so that when I square this, it's not going to be too big. All right, so to find out what our y value is, we are going to square each x value. So x squared, in this case, our x is -3, so we're calculating -3 squared. That's -3 times -3, which is +9. Then we'll do the same thing for -2. So -2 squared is +4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So these are our set of points that we can graph to create our quadratic graph. So it's important that you always label your graph when you are graphing. So I'm going to label our x-axis and our y-axis. So our y-axis is the highest number that we have in our table of values is 9. And if we count by ones, it is going to be higher than what we have available to us for our y-axis. So it's okay. I'm just going to go up to 4 instead. I'll just omit the -3, 9, and then 3, 9. With those amount of points, we're going to get an idea of what this graph is going to look like anyway. Okay, so now I'm going to graph -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And then I'm going to connect these points. And because we just picked a few points, this graph can have an infinite amount of values for x, meaning that it could be any x value out there. So we could have picked 100 if we wanted to. And we need to show that this graph is a function over any sort of x value. So I'm going to indicate that by having 0 arrows on either side of my arms. And this shows that this graph can go on forever. So this is our graph. It kind of looks like a U shape in a sense, and it'll always basically look like that. It could also look like an upside down U shape because it'll be flipped. You'll see that eventually. It also looks symmetrical. So if I don't want to split this graph to see what the mirror is going to be like, this would be my mirror line, all the way, the vertical line all the way down the middle. And that just means that my graph on one side is going to be mirroring the graph on the other side. So this side on our left side should look the same as the other side. It's just mirrored on the other side. So your parabola is always going to be symmetrical like that. And I've been using the word parabola because every quadratic function is a parabola. You can interchange those terms. You can call it quadratic function or you can call it parabola. So here are some fun characteristics. The vertex is a highest or lowest point. The vertex is a minimum if the graph opens upward, and the vertex is a maximum if the graph opens downward. So in this case, our vertex here is a minimum, and it's that point here because it's the lowest point, lowest y point that we have. So your vertex is located at 0, 0, and those are the coordinates. And we have a minimum here because we have a lowest point, but we don't have a maximum. We don't have a highest y point. Now, if a graph opens downward, it's going to look like this, and that is when you're going to have a maximum, and that is also your vertex. So it's just saying the parabola is symmetrical, and this green line that I just drew, this is called the axis of symmetry. It's a vertical line that kind of cuts right down your quadratic so that it looks the same on each side. Now your domain is all possible x values. Usually we would say that the domain is where the function is defined for your most left x values and then your most right x values. So we're just going to use interval notation for this. Generally, interval notation is the easiest one to use. There's also set notation that you could use as well. And in the beginning, I'm going to show you both, but it'll be ultimately up to you which one you want to choose. So for interval notation, we're just going to state from left to right what is the most left x value we can have and the most right x value we can have. So because we have an arrow that's pointing towards negative infinity, because this can go on forever, our most left x value is going to be negative infinity. So again, with domain, we read from left to right for our x values. And then if we look at our right side, we are going towards infinity because of this arrow. So then that is the other part of our domain. Notice that I have round brackets here. That's because we can never touch infinity. So we have round brackets because we never touch that point or that place. Another way you can write it is set notation. So because we're talking about x values, we can state that x is a part of or is an element of, and then we're going to say what set. So x can be in the set of the real numbers. So R, that's an R for the real numbers. And what this is saying that x can be any number out there as long as it is a real number. So it can be an integer, it can be a whole number, it could be a fraction, it could be a decimal, but it just can't be an irrational number. So all your problems are going to have this domain, and then you just pick one or the other to state, either negative infinity to positive infinity or x is element of the reals, and you just write that only. All parabolas will have this domain. The only thing that would change is your range, depending on where your vertex is. So my lowest point in terms of the y values is going to be at 0. And now I'm changing my bracket because we actually touch this on the graph. So we actually touch y equals 0 as an actual point on this graph. That's why I have a square bracket now. Now reading from the most bottom point, so for your range, you're going to read from bottom to top. So our lowest point in terms of our y value is located at 0, y equals 0. And then if we go up, we have an arrow that's pointing towards infinity. So it's just going to keep going. It's going to keep going higher from there. So then the other part of our range is going to be infinity. And again, we won't ever touch infinity. So we have a round bracket. If you want to state this in terms of set notation, we're talking about the y values. So we're going to use y now. And in this case, y has to be greater than 0 because we don't have any values that are smaller than 0. But it can be equal to 0 as well because that's a point. And then we could say where y is an element of the real numbers. So you can state it as either interval notation or set notation. I think that interval notation is easier to use in set notation, and in pre-cal 40, you can use both again, but it's more common to use interval notation than set. Okay. Moving on to our very first example with all those characteristics, we're going to try to analyze this now. We've been given this graph, or we've been given the equation to graph, and then we want to determine those 5 different characteristics. So to graph this first, we're going to use our table of values, and the x values were given to us. Now, we technically don't need all these points to graph our parabola. You probably just need 3 points in order to graph your parabola and then get a good idea of where your shape is. As long as you have the vertex and you have 2 other points, you should be good to go. So I'm going to start off by trying to find our y values for these. I might not do them all because you will see a pattern with your y values eventually. But let's do x equals -4. So I'm going to plug -4 into the equation that was given to us. So it's x squared, so -4 squared plus 2 times -4 minus 3. If you do this calculation, this will be 5. If you can stay away from the calculator when you're doing this, that would be great. Just because in grade 12, you don't use the calculator very much, so it's better for you to practice now rather than struggling next year when you are not allowed to use the calculator. Okay, so the next one is going to be -3 squared plus 2 times -3 minus 3. If you simplify that, that's going to be 0. And then I'll just give you the other points. So -2, you plug that in, you're going to get -3. Put in -1, you're going to get -5. Plug in 0, you're going to get -3. So if you take a look, we already kind of have a pattern going on because I have a repeating y value right here and right here. So it's safe to assume that my next one's going to be 0, and the next one for x equals 2 is going to be 5 because we know our quadratic is symmetric. And then we could just disregard these points because we don't really need them. Okay, so let's graph this, but first we have to label our axes. All right, so our first point is -4, 5. Then we have -3, 0, -2, -3, -1, -5, 0, -3, 1, 0, and 2, 5. So we're going to connect our points. And add arrows on each end. About the shape of this graph, be careful not to make it too straight looking, meaning your arms kind of look like this, and then you have a pointy vertex, and then go back up, because that's a completely different function. You want to make sure that when you're drawing your parabola, it's as curved as possible. So this is your general shape of a parabola, something like this, okay? So just be careful how you connect your points, because it does matter. All right, so we're done drawing our parabola. Now we're going to analyze the characteristics of this parabola. So we want to look for the x and y intercepts. So your x-intercepts are points on the x-axis. And we just generally state what that value is. So on the x-axis, we have an x-intercept of 1 and a -3. Your y-intercept is found similarly, but in this case, we're going to read the y-axis. So we have a point over here, down here, at y equals -3, so your y-intercept is at -3. The next we're going to find is the vertex. So this is either your minimum or your maximum. In this case, we have a minimum. Our lowest y point is going to be down here, and it has coordinates -1, -5. Your axis of symmetry is always going to be the x value in your vertex. But we're going to state this as a line, because if I were to draw in the axis of symmetry, it is a vertical line that cuts right through the parabola. And to describe this line, we're going to use an equation to describe it. So this is x equals -1. That's the equation of that vertical blue line I just drew. And again, it's always going to be the x value of your vertex. The next thing we're going to find is domain. So remember that domain has the same domain for all quadratics, which is -infinity to +infinity. And then your range, we're going to read the lowest y point to the highest y point. So from down to up, our lowest y value is -5, and we touch it, so it's a square bracket, and it goes on to infinity. So let's just say that we can't identify the x-intercept on a table or a graph, meaning that if I were to put in these table values, I don't actually get an x-intercept. Or once I graph it, it doesn't look like it lines up or in between like a -3 and a -4, and I don't really know what that value is. I just can't assume it's -3.5. We can actually find the real value. So in x-intercepts, we always know it has to be on the x-axis where y is equal to 0. So x-intercepts occur when y is equal to 0. So that means we can set y equal to 0. And then we want to solve for this. So to solve for this, we're going to factor. So your factors of 3 are 3 and 1, and to get a +2, you need a +3 and -1. So then your x-intercepts, or your x values, are going to be at -3 and at 1. And those are your x-intercepts, and that's it. So these x-intercepts are also called zeros of the function, because these are the values of x when the function is 0. And the zeros of the function are the roots of our quadratic equation. So please take a note of these terms because they will be used interchangeably. If you can't find the y-intercept, then in this case you're going to set y to 0 and then solve for it instead. So if you're looking for the x-intercepts, you set y to 0. If the y-intercept can't be identified, you need to set, sorry, this is a typo, you need to set x equal to 0 and solve for it. Okay, so if you need to find the y-intercept, then you're going to set x to 0 instead. So for example, for this one, if you want to find the y-intercept for this previous question, you're going to set x to 0, so that's 0 squared plus 2 times 0, so that means your y-intercept is going to be -3. That's how you would solve for your y-intercept. And the last note here before I end this video, if you ever need to write a quadratic equation in standard form, which looks like this right here, you would just expand and simplify. So for example, let's just say I have something like this. What you need to do is expand this x plus 2 squared. You do x times 2, then 2x, and then 2 times 2. And then afterwards you collect your like terms to figure out what that would be in standard form, because that's one of the questions in your homework. So please work on page 17, questions 1 through 3.